Flipped classroom video for further maths unit 2. Discrete random variables. A random variable is a verbal description of a rule for assigning a numerical value to every outcome of a random experiment. A random variable will be denoted by a capital letter close to the end of an alphabet, as in W, X, Y, or Z, and an arbitrary observed value of that experiment will be denoted by the corresponding lowercase letter. So for capital W, we'll have an element small w. Example 1. Consider the random experiment in which a coin is tossed 3 times. The sample space, i.e. all observable outcomes, would be 3 heads, head, head and a tail, head, tail and a head, tail, head and a head, head, tail, 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 head, tail, 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 head, and tail, tail, tail. 2 possible random variables to associate with this experiment could be 1, the number of heads tossed, so we could be counting that. It could be 0, or 1, or 2, or 3. The difference between the number of heads and the number of tails tossed. So having possible values, well, either it's 3, if there's 3 heads there'd be no tails, so the difference between them would be 3, or 1 if there's 2 of one and 1 of the other, so 1 and 3 would be the possible values of y. Example 2. Consider the random experiment in which a coin is tossed until a head is obtained. Let Z denote the number of tosses made. Then the possible values would be 1 toss and you'd get a head, or 2 tosses before you get a head, and so on. So that could go on forever. Example 3. Consider the random experiment in which a hand of 13 cards is dealt from an ordinary pack of playing cards. So out of 52 cards, we have dealt a hand of 13 cards. 2 possible random variables in this case are the number of red cards dealt. So we'd have no red cards up to 13. The number of aces dealt, so that would have 0, 1, 2, 3 and 4. In each of the above examples, the possible values of the random variable can be listed individually. Such a random variable is said to be discrete. We have discrete, separate values of the data collected. The distribution of a discrete random variable. Having listed the possible values of a random variable, the next step is to determine their probabilities of occurring. And when doing so, always check that the probabilities add up to 1. If x is a possible value, x, little x, of a random variable big X, we write the probability of big X is equal to little x for the probability that the observed value of capital X will be little x. The specification of all possible values of x and their corresponding probabilities is referred to as the distribution of x. So all possible values of x and their probabilities is called the distribution of x. More strictly, it is the probability distribution of x, since 1 unit of probability is distributed over all the possible values of x. They must add up to 1. A fair coin is tossed 3 times. Find the distribution of the number of heads tossed. Remember, the distribution is the total possible outcomes with their corresponding probability. So the sample space are the ones we did in a previous example. Since the coin is fair, these 8 outcomes are equally probable. So each of these outcomes will have 1/8 probability, half head, half of the other head, half of the third. So half cubed would be 1/8. Let x denote the number of heads tossed, then the possible values are going to be no heads, 1 head, 2 heads, and 3 head. X is not occurs if no head is tossed, that is, if the outcome is tail, tail, tail. It follows that the probability of x is not is 1/8. If x is 1, occurs if 1 head is tossed, that is, the outcome could be head, tail, 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 head, tail, or tail, tail, head. So that the probability of x is 1 would be 3/8, because we've got 3 possibilities, and they're all equally likely. Similarly, we find that x is 2, 2 heads is also 3/8, and x is 3, which is 3 heads, is 1/8. So we write that in a table. So there's our x values on the top, and the probability of each of those x values is given below, and we check that they add up to 1, and they do. So that is the distribution of the number of heads tossed. Another example, 4 balls are drawn without replacement from a bag containing 7 red balls and 6 blue balls. Find the distribution of number of red balls drawn. So we need to define what our red ball is going to be. So let x be the number of red balls. And then x can have values no red balls, 1, 2, 3 or 4. Remember, we are choosing 4 red balls from the bag. So x is not would be no reds and 4 blues, and the probability of working that out would be the number of ways of choosing no reds and 4 blues out of the number of ways of choosing 4 out of a possible 13 altogether. So we can work that out. Remember our combinations formula. We can also use a calculator for them. So we've got 7 red balls and we want to choose 0, and we have 6 blue balls and we want to choose 4 of those. Out of a possible 13, choose 4. So we can work those out, and we've got 1 for the 7, choose 0, 15 for the 6, choose 4, and 7, 1, 5 for the bottom. If we don't cancel, we can see that they add up easily. So I would suggest we leave the bottom as it is and just work out the top for each one. So probability of x is 1. So we've got 1 red and 3 blues. So 7 choose 1 and 6 choose 3 out of a possible 715 ways, giving us 7, 20 for the 6 choose 3, and that gives us 140 over 715. X is 2, so we've got 2 red balls and there must be 2 blue balls. So 7 choose 2, 6 choose 2 out of a possible 715, giving us 21 times 15 for the top, giving us 315. X is equal to 3, so we've got 3 reds, 1 blue, 7 choose 3, 6 choose 1, gives us 210. And 4, so 4 reds and no blues, we have to work them all out, and we get 7 choose 4, 6 choose 0, giving us 35 out of 715. Add all those up, and they do add up to 1. We can write them in a table. So x was no reds, 1 red, 2 reds, 3 reds and 4 reds, and we worked out their probabilities, which sum to 1. So that is the distribution of the number of red balls. Now the expected value of a discrete random variable, denote the possible values, the observed values are x1, 2, and so on up to k with corresponding frequencies. Then the mean value would be the sum of each x with its frequency divided by the sum of f. The relative probabilities of each xi occurring is the frequency of that at xi, how many times it's occurred, over the total possible. So each pi, the probability of each xi occurring, is the probability, is written as each xi belonging to x occurring, the probability of that occurring. So we can now write the mean as, instead of x1 f1 and then divided by the total frequency, it's going to be x1 p1, x2 p2, and so on up until xk pk. So we have the mean as being x times the probability of that x occurring, and we write that as e of x. The expected value is the mean of x. Find the expected number of heads that will be obtained when a fair coin is tossed 3 times. Now we've already done this example before, so we've done the distribution. Let x denote the number of heads that will be obtained, and that was our distribution. So for no heads, 1 head, 2 heads, 3 heads, we had those probabilities. Now we want to work out the expected number of heads occurring. So you need to multiply each x with its relative probability. So 0 with 1/8 plus 1 with 3/8 plus 2 with 3/8 and 3 with 1/8. Add those up, multiply them, add them up, and we get 12/8, which is about 1.5 is the expected value. It's symmetrical, so you would expect it to be in the middle anyway. So the mean or the expected value of that distribution is 1.5. The other example we did, 4 balls are drawn at random without replacement from a bag containing 7 red balls and 6 blue balls. Find the expected number of red balls that will be drawn. So we've done the distribution. X is the number of red balls. The distribution came to this. So what is the expected number of red balls? The mean is each x multiplied by its relative probability. So 0 multiplied by 15 over 715, 1 multiplied by 140 over 715, and so on. And we get 1540 over 715, which cancels down to 28 over 13, which becomes 2 and a bit. So our mean is in there somewhere. They're discrete, so you only have whole number values anyway. The expected value of a function now of a random variable, because we need a method to work out the variance. So if we want, if x denotes some function of the discrete random variable x, whose distribution has got the probability, relative probability for each x, then the expected value of hx is, of a function now, is the sum, or the expected value of hx is h times the probability, h of x2 times the probability. So it's the sum of h of each value of x times its relative probability. And when the function is just x, this reduces to the expression we had for expected value of x for the mean earlier. So we are interested in expected value of x squared. So that would be sum of each x squared multiplied by its probability. If we wanted the expected value of 3x minus 1, I would have to take each x, multiply 3 by 3, take away 1, and multiply the answer by its probability and add them all up. The variance is what we're interested in. So the variance of x is defined to be the sum of each x minus the mean, all squared. So if we expand the bracket there, we've got x squared minus twice x times mu plus mu squared. I can take the expectation in. Mu is a constant, so it's the expected value of x squared minus twice expected value of x times the constant mu plus mu squared. But mu is the expected value of x, so I've got minus 2 of the expected value of x squared plus expected value of x squared, which gives us e of x squared minus e of x all squared for the variance. So the variance is worked out that way. Example 9, the 4 balls experiment again. Find the distribution of the number of red balls drawn and determine the mean and the standard deviation of the distribution. We've done the distribution, we got the distribution to be that, we got the mean to be 28 over 13, the expected value. So for the variance and the standard deviation, we need to work out e of x squared. So square each x and multiply by the various probabilities, and I get an answer of 70 over 13. So the variance is defined to be e of x squared minus e of x all squared, so 70 over 13 minus the mean 28 over 13 all squared, which gives me 126 over 169. We need the standard deviation, so I need the square root of that, which is about 0.863. A past paper question. The probability distribution of the discrete random variable x is given by that probability for each of those x's and 0 otherwise. And show that k is 1/9. We'll do that first. Now you need to set up the table for each of these values. So if x is 1, our probability for x is 1 would be 2k. Similarly, for x is 2, we've got 2 and 1, 3k. And for x is 3, we've got 3 and 1, which is 4k. Now you know that this adds up to 1. So if I add these up and sum them to 1, I get that 9k is equal to 1, so k must be 1/9. Find the expected value of this distribution. So it's each x multiplied by its probability. So it's 1 times 2k plus 2 times 3k plus 3 times 4k becomes 20k. I know that k is 1/9, so it's 20 over 9, which is about 2 and 2/9, so it's within there somewhere. Evaluating expected value of 1 over x. Now remember, for a function, it's 1 over each value of x times its probability and add them up. 1 over 1 times the 2k, 1 over 2 times 3k, plus 1 over 3 times 4k becomes 29 over 8k. K is 1/9, so it's 29 over 54. Another example, last one. The discrete random variable x has the following probability distribution. So you're given the distribution this time. Find the range of possible values of the constant theta. Remember, they need to add up to 1, and they do. So theta and 2 theta is 3 theta. Add 1, take away 3 theta, and we've got 1. But each one has to be between 0 and 1. So we have, for the first value, theta's got to be between 0 and 1. For the second value, we have theta being less than a half. So 2 theta is less than 1, so theta will be less than a half. And for the third value, we need, have a look at the 0 value this time. So 3 theta has to be less than 1. So theta has to be less than a third. So that's our value for theta. So that's the range of values for the constant theta. So you need to look at each separate one and see what follows. Less than a half, but less than a third is smaller. Given that the expected value is 2.2, show that theta is 0.2. So expected value is x times each probability, and you're given it's equal to 2.2. So 1 times theta plus 2 times 2 theta plus 3 times 1 minus 3 theta. Multiply those out, collect terms. The 3 can go over, so we have 0.8 is equal to 4 theta. We have minus 4 theta here, plus 5 theta minus 9 theta. So eventually we've got theta is equal to 0.2. Standard deviation, so we need the variance, so we need the expected value of x squared. So expected value of x squared is x squared times its probability. So 1 squared times theta plus 2 squared times 2 theta plus 3 squared times 1 minus 3 theta. So we've got theta plus 8 theta plus 9 minus 27 theta, giving us 9 minus 18 theta. Theta is 0.2, so that becomes 5.4. So the variance is e of x squared minus e of x all squared. So 5.4 minus 2.2 all squared, which becomes 0.56. Then the standard deviation is the square root of that, which is 0.748. Last bit, evaluating expected value of 1 over x. So we want 1 over each x times its probability. So 1 over 1 times theta, 1 over 2 times 2 theta plus 1 over 3 times 1 minus 3 theta. And we get theta plus the third minus theta. We know that a theta is 0.2, giving us the expected value of 1/8 to be 8 over 15. I put 2/10 instead of theta here. And that's the end of the video on discrete random variables.